Okay, so this talk is on shrinkage of decision lists and DNF formulas. So I'm going to start by reviewing the models of computation that I'll be discussing. So first are DNF formulas. So DNF is a disjunction of clauses, so C1 to CM. So each CI is a conjunctive clause, also known as a term. For example, X2 and not X3 and X6. A decision list is a sequence of M clauses and M output values, so such that the disjunction of the clauses is a DNF tautology. So it is true on every input X. In other words, for every X satisfies at least one of these clauses. And the output values B1 to BM can be anything. They don't have to be Boolean values necessarily. So the function computed by a decision list is as follows. So on an input X, the output is BI, where I is the first index for which the clause CI is satisfied. I will also be discussing decision lists and De Morgan formulas. I assume everyone's familiar. Here's some pictures. Good. So associated with these models of computation, we have the following complexity measures. So let f be any function on the hypercube. Again, not necessarily Boolean valued. We can define its decision tree size and its decision list size, denoted dt of f and dl of f, where we measure size of decision tree by the number of leaves, so the number of output nodes, and decision list size by the number of clauses. I didn't mention before, but so without loss of generality, you can always take the final clause in a decision list to be the empty clause, but we still count that toward size. For Boolean valued functions f, we additionally define the minimum number of clauses in a DNF formula that computes f, and L of f, it denotes the De Morgan formula leaf size of f. And so these various complexity measures also have a width or depth version, and they satisfy these kind of inequalities. In particular, note that under our way of defining things, decision list always has at least one clause in it, and the decision list size is at most decision tree size. In particular, every decision tree can be converted to a decision list with the same size. Okay, and yeah, and you can think of these as sort of DNFs and CNFs are also special cases of decision lists, and these are all you could think of this as a version of depth 2 unbounded Fanon formulas in some sense. All right, so the P random restriction. So a restriction is a partial assignment of the variables of a Boolean function to value 0, 1. And star denotes that a variable is left undetermined. So for a parameter P in 0, 1, we denote by R sub P the P random restriction, which fixes each variable to 0 or 1 with equal probability, so probability 1 minus P over 2 each, and leaves the variable unrestricted with probability P independently. And for any function f, we denote by this f harpoon RP, the restricted Boolean function on the subcube associated with the restriction. Okay, so it's very well established that the P random restriction simplifies these very small, low complexity measures like De Morgan formula size and DNF, CNF formula size. So in the case of De Morgan formulas, over a long line of work, we now know tight bounds on the so-called shrinkage of De Morgan formulas. So you look at the expected leaf size of formula of a Boolean function f under RP, and this shrinks like p squared times the formula size of f. And when p is very small, it shrinks like p times square root of the leaf size of f. Okay, and I mean, to show a shrinkage of P times L of F is trivial. So this P squared says you're shrinking faster than what you'd expect just looking at each leaf. Another example of how RP simplifies formulas is the switching lemma. So this is more than just shrinkage in expectation. This gives a tail bound, but it's not in terms of size. Rather, it's at least in the original version of the switching lemma is in terms of width. So if I have a small width DNF formula, and I hit it with a random restriction for sufficiently small p, then I look at the resulting CNF width, and you get an exponential tail bound on that quantity. Okay. That slide's repeated. Good. So, right. So here's the results of this paper. So first of all, I first state a sort of what I believe is a folklore result, although I haven't found a reference. This is a very simple proof that the decision tree size of F under P random restriction in expectation is at most the decision tree size of F raised to the power log 2 of 1 plus P. And this bound is actually tight in certain cases. I believe when F is a parity function, this is actually completely tight. So our main result is stated below. It's a similar looking upper bound on the expected shrinkage of decision lists. Okay, so instead of this log to 1 plus P in the exponent, we get slightly larger function of P. So log base 2 over 1 minus P of 1 plus P over 1 minus P. And we get this for decision lists. So it's saying that the shrinkage of decision lists looks like decision trees, even though decision lists are a more powerful model. And we get, but the same proof gives the same bound if you replace decision list size by DNF size plus 1 or CNF size plus 1, and we get the same bound. Okay, and so this exponent as a function of P, this is plotted above, and the thing to note here is that when P equals, so this is a increasing function, it's 0 when P is 0, it's 1 when P is 1. And in particular, when P is less than 1, we get a bound which is non-trivial. Right, so making this more quantitative, so if F is a function, any function with decision list size M, then we get the following bounds on the decision list size of F under P random restriction for various settings of P. So when P is very small, so when it's order of 1 over log M, okay, then we get a bound of 2. All right, and if you want, but even taking P just to be a constant, so if P in particular is root 5 minus 2, then our theorem implies that the decision list size and expectation is like square root of M. And then, if you wanted to shrink down to half the size, then you can take P actually very close to 1. Okay, so a remark here is that the switching lemma actually implies something stronger than this when P is very small. So when P is order of 1 over log M, then the switching lemma, you can use the switching lemma to show that the expected decision tree size is at most 2. Okay, and since decision tree size is larger than decision list size, this is an even stronger result. However, the switching lemma, at least the Hostad's version of the switching lemma, doesn't imply anything at all in the, when P is larger than 1 over log M. So in particular, it doesn't imply anything in the regime where P is constant or where P is close to 1. And this is known as the so-called mild random restriction regime, and it's important in applications to de-randomization and Boolean analysis. So yeah, so we expect our result might have some applications, since in particular for large values of P. Good. So to give some perspective on the result, I think it's useful to draw this distinction between size measures and the corresponding width depth complexity measures. So here I've stated, first on the top here, I've stated Hastad's switching lemma. Okay, earlier I stated it in terms of CNF width to DNF width, but a more general version in terms of decision lists and decision trees is the following bound. It doesn't really matter what it's saying, just we get some bound on the tail bound on the decision tree depth of the restricted function in terms of the decision list width of the original function. So in a paper a few years ago that was a precursor to this current paper, I proved a version of the switching lemma in which decision list width is replaced by log of decision list size. And I didn't mention before, but for each of these size measures, for decision trees, decision lists, even De Morgan formulas, the corresponding width or depth measure usually bears some logarithmic relationship here. So, right. And okay, so another result on which this current paper builds is from a recent paper of Lovett, Wu, and Zhang, where they prove a shrinkage-like result for decision lists, well, in terms of the decision list width of F. So their result states that the expected decision list size of F under a P random restriction is bounded by 4 over 1 minus P raised to the decision list width. Okay, and so here I've just rewritten our result, putting the decision list size in the exponent. This is the same bound as in our main theorem stated here. Anyway, so the point is here we're doing something. Our result stands in relation to Lovett, Wu, Zhang's result in a similar way that our switching lemma relates to Hastad's switching lemma. That is, we replace decision list width with log of decision list size. Okay. So let me say something very briefly. I mentioned that this bound on the shrinkage of this decision tree size is it's just a very, very simple inductive argument. I mean, this is the entire proof right here. I'm not going to go through it, but it's based on convexity. It uses Jensen's inequality. And yeah, we also use some Jensen's inequality, something like an entropy type inequality. So I'm not going to really say anything much about the proof of our shrinkage bound for decision lists. Rather, I'm going to prove for you a related bound that contains all the essential ideas. Okay, so, and one key definition is the index function associated with the decision list. So, okay, let L be any decision list of size M. And recall this means that the disjunction of clauses C1 to Cm is a DNF tautology. B1 to Bm are arbitrary output values. So I'll denote by index sub L the function which maps an input in the hypercube to the first index, the index of the first satisfied clause. Right? And so in other words, the function computed by L of x, is just equal to the output value B at the index L of x. Okay, and one observation is that without loss of generality, we can assume that the index function is surjective, is onto. Otherwise, if it wasn't, then you could simply just delete from L any pair CI/BI, where I is not in the image of the index function. And in doing so, you'll still have a DNF tautology, and you'll be computing the same function. And then the way that the expected decision list size under a P random restriction, the way that that's bounded in this paper of Lovett, Wu, and Zhang, and also in our paper, is just by using this observation, from which it follows that for any restriction rho, the decision list size of L under the restriction rho is at most the size of the image of the index function of L under rho. Okay, so the way that yeah, I'm not going to say anything about the proof of our bound on shrinkage, but let me instead show you something related that's simple and I can fit the proof in one slide essentially. So we continue to fix a decision list L, and we're going to consider the following probability distribution. Simply the mu. I guess I could have simply written this as mu I is just the probability. So this here is just the probability that in that index L of X equals I. All right, and note that that this value mu I, well, of course, this is a distribution, it sums to 1, and each mu I is at most 2 to the minus the width of Ci, the size of Ci, so the number of literals in this clause. So okay, so what I'll show you now is a simple calculation that shows that the average sensitivity of the function computed by L is at most twice the entropy of this distribution mu, which is at most twice log m. Okay, and this calculation is going to be similar to our shrinkage bound in some ways. All right, and I mean, here it is all on one slide. I'll just go through it very quickly. So this first line here is just the definition of average sensitivity. It's the expected number of coordinates j and 1 to n, such that you know, flipping the jth coordinate of the input changes the value of the function computed by L. So then the next line is just by linearity of expectations. In fact, I guess this should even be equality. Yeah, and right. So and note that, okay, so if L of X is different from L of X with its jth coordinate flipped, this means that the associated index, the index function is also different on X and X with its jth coordinate flipped. Okay, and in particular, this means that, you know, one is less than the other. And so you can easily show that this is, okay, I guess the inequality belongs here. This is at most twice the, this is missing a summation here. So we'll, so sum over I equals 1 to m. Right, so this event breaks up into the probability summed over clauses I and variables j, the probability that that index L of X equals I and index L of X flipping its jth coordinate is bigger than I. Okay, so we pull out, we split up this probability into the probability that index L X equals I, which is just mu I, and then we have this conditional probability over here. And then the observation is that this conditional probability here is 0 whenever I is not, a variable occurring in the clause Cj, and obviously this probability is at most 1 otherwise. But then summing over all pardon me, summing over all the variables, the contribution that we get from here is at most just the number of variables in Ci. And then we use our, earlier we noted that mu of I is at most 2 to the minus size of Ci. So that gives this bound here. And now we have just the expression for the entropy of mu. So this equals twice the entropy of mu. And since mu is a distribution with support size m, this is at most twice log m. Okay, so that's this simple proof. And all I'll say about the proof of our shrinkage bound is that we define a different distribution, okay, something similar to mu I, but it, instead of being generated by X, it's generated by P random restrictions. And it's a little bit subtle actually how you define it, but the essence of the proof is already in this calculation that we saw here. Good. So to wrap up here I've just stated our bound again, our shrinkage bound for decision lists. So one open question you can ask: what is the best constant, okay, C sub decision list for which the shrinkage, the expected decision list size of F under RP is order of decision list size of F raised to the power C dl times P. And in the paper we show, well, okay, so our main result gives the upper bound that this constant's at most 2 over natural log of 2. And we can also show it's lower bounded by the corresponding constant for decision tree size, which is exactly equal to 1 over natural log of 2. In some sense, this constant here is really should be thought of as the shrinkage exponent in the setting of decision list size. Another further question raised by our work is, what is the shrinkage of depth 2 AC0 formulas? And our results for CNFs and DNFs settles the case D equals 2. And we conjecture that for any constant D, that the bound on the expected formula, depth D formula size of F under RP should be at most the depth D formula size of F raised to the order of P, P to the 1 over D minus 1. Okay. And so this is what we prove in the case D equals 2. This is just order P. And this is what you would predict based on the formula size of parity, under the hypothesis that parity is the most shrinkage resistant, formula of a given size. Okay, so thank you.